Welcome to another video of Controllers Tech. This is yet another video on register-based programming series, and today we will see the DMA STM32F103C8. Some users reported that they can't get the DMA to work with the blue pill, so I decided to make a separate video on it. I will demonstrate the working of DMA with the UART. UART have already been covered with F4 series MCUs, and here is the main file from that. The process is almost identical, and that's why I will not go into very deep today. You can check out the other video for more detailed steps. We will use the same steps for blue pill, with the addition of DMA of course. So let's create a project with Kyle. Select the CM/sys core, and the device startup files. Here first of all we will include the device header file. Now we will write a function to configure the UART. Here are the steps to configure the UART with DMA. They are identical to that for the F4 series we discussed earlier. Enable the clocks, configure the pins, enable the UART, define the word length. Here we will also enable the DMA for transmit, or receive. This is the additional step. Then we will set the baud rate, and enable the transmitter or receiver. I am going to use the UART2, so the pins PA2 and PA3 will be used. Here is the entire program for it. First we will enable the UART clock, and the GPIO clock. Then we will configure the pins for the alternate function. This configuration of pins is a little different in the blue pill, as compared to the F4 series. Let's see it in the reference manual. We need to check the GPIO configuration for the device peripherals. Here we have the UART section. For transmit in the full duplex mode, the pin must be set as the alternate function push-pull. And for receive, it must be set as the input floating, or pull-up. To set these modes for the pins, we will check the configuration register. Here we have alternate function output push-pull, 1-0. And the output mode at maximum speed is 1-1. So we are setting the pin PA2 as the output push-pull. And the pin PA3 in the input mode. Let's see how to enable the internal pull-up for the pin. Here is the table. As mentioned here, for the internal pull-up, the output data register must be high. Next we will enable the UART, and then configure the DMA for the transmit, or receive, or both. Here is the UART control register 3, and the bits 7 and 6 controls the DMA. I am only enabling it for the receive. Next is the setting of the baud rate. The formula is the peripheral clock, divided by the 16 times the UART division. If you rearrange the formula for the desired baud rate, you will get the values of the mantissa, and the fraction. This is explained in the previous video, so I am not explaining it again here. Anyway, this will set up the baud rate of 115,200, while the peripheral clock is running at 36 MHz. You can check which clock is connected to the UART in the clock diagram in the datasheet. Finally, we will enable the transmitter and the receiver. This is it for the UART configuration. Now we will initialize the DMA. Before initializing it, we need to check which channels will we be working with. Here we have the table for DMA1 requests. You can see, the UART2 receive is connected to the channel 6 of the DMA1. So we will write our initialization according to that. First we will enable the DMA1 clock. Now for the rest of the configuration, we will check the DMA registers. The first register we have is the interrupt status register. The bits here are read-only bits, and they indicate the status of the interrupt, which was triggered. Next register is the interrupt flag clear register, and this register is used to clear the interrupt bits that were set in the previous register. Next we have the channel configuration register. Let's start from the least significant bit. The first bit is to enable the DMA, and that we will do in the end. Then the next 3 bits are interrupt enable bits, and we will enable all 3 interrupts this time. Next is the data direction. As we are copying data from the UART peripheral to the buffer in the memory, we will keep this bit 0. Next is the bit to enable the circular mode, and yes, we will enable the circular mode for the DMA. Next bit indicates whether we want to increment the peripheral address. Since we are copying the data from the data register of the UART, we don't want to increment the address of the peripheral. But we will increment the memory address, so that the new data is copied in the new location. Next we have the data size for the peripheral and the memory. Here we will use 8 bits, as that's how the UART is set up. Next is the priority for the channel, and we will keep it low. This is an important bit, if you are using more than one channel. You can control the priority of the respective channel. This is it for the initialization of the DMA, but we still need to configure it, and we will write a new function for that. This function takes 3 parameters, the address of the source, destination address, and the size of the data. The next register we have in line is the number of data register. This register stores the number of data item that we want to transfer. This is a 16-bit register, so we can transfer up to 65,535 values using the DMA. Once the transfer is complete, the register will stay at 0 if the normal mode is selected. But if the circular mode is selected, the value in the register will be auto-reloaded to the previous value, and this way transfer never finish. This is how the circular mode of DMA actually works. Next is the peripheral address register, and here we will write the address of the peripheral. In this case, the source address, since our source is the peripheral itself. Next we have is the memory address register, and in our case, it will be the destination address. This will set up everything in the DMA, so finally we will enable the DMA. This is done by writing the bit 0 of the control register 1. This is it for the DMA part. Now we will write a callback function for the DMA interrupts. The callback function are defined in the startup file, and we need this one, DMA1 channel 6 handler. Once the interrupt is triggered, we need to check whether it's half transfer interrupt, or full transfer. This can be done by checking the DMA ISR register. Here you can see, we have bit 22 for the half transfer interrupt, 23 for transfer error, and 21 for transfer complete. Based on which interrupt is set, we can do the rest of the processing. Let's define some buffers first. Here, if the half transfer interrupt is set, we will copy the data from Rx buffer, starting from the first position in the buffer. The size of the data will be half of the Rx buffer, since that's the data which arrived in the buffer. After copying this data, we will clear the interrupt bit by writing the respective IFC or register value. This register is used to clear the interrupt bit, set in the ISR. We will update the index, and if it is more than the main buffer size, we will reset it. Similarly, if the transfer complete interrupt bit is set, we will copy the other half of the Rx buffer. After copying the data, we will clear the transfer complete interrupt flag. This is a good advantage circular mode have. While we are handling the first half of the buffer, the second half is receiving the data. Even if the data arrives during the copying process, it will be saved in the buffer. This way the data is never lost. Once all the data is received, the DMA will reset the counter to the original value, and prepare itself for the new data. And all this happens place without affecting the CPU. Now we will write the main function. Let's initialize the system. As I mentioned this in the previous Blue Pill video, that by default the MCU will be running at 72 MHz, and we are okay with it. Now configure the UART. Initialize the DMA. And now we will call the DMA configuration. Here source address is the address of the data register of the UART, as that's where the data is going to arrive. Destination address is the address of the Rx buffer. And the size is the size of the Rx buffer. I forgot to set the interrupt. We will set it before configuring the DMA, as the DMA will start as soon as the configuration ends. First we will set the priority of the DMA1, channel 6 interrupt. And then we will enable the interrupt. So that's all, now it's the time to test it. I will set a breakpoint in the half transfer callback. I am sending this 1 2 3 4. For some reason, it's not displaying here, but it's being received, don't worry about it. Remember that the RX buffer size is set to 20 bytes, so nothing happens until I send at least 10 bytes of data. And now we have got it, he hit at the breakpoint. DMA was set to receive 20 bytes, and as soon as it received half the data, the half transfer interrupt was triggered. Here you can see all the 10 bytes of data. Now let's transfer again. Notice that nothing will happen until we receive the full 20 bytes. Another hit at breakpoint, and this time the transfer complete interrupt was set. Now we will run again, and the new data has also been copied to the main buffer. Let's try to send the 20 bytes at the same time. Something weird is going on with the Kyle today. Let me try one more time. It received it this time. And here you can see the data is copied to the main buffer also. Don't worry about those glitches you just saw, it was some connection issue. Let's do one last test, and this time I will send 12 bytes. So we have 12 bytes of data in the RX buffer, but only the 10 bytes were copied to the main buffer. I guess you understand why this happened. The half transfer interrupt was set after the 10 bytes, so only the 10 bytes will be processed. But this does not mean that we lost the 2 bytes. Those 2 bytes will be copied next time. Let's send the same data again. You can see, in the 10th and 11th positions, we have those 2 bytes, which was left out the last time. Well, that's how it works. Like I said few minutes ago, the data is never lost in the circular DMA. The bytes remain in the buffer, and can be handled in the next interrupt. Even when we are processing the first half of the buffer, the data can still be saved in the second half. And this is the entire purpose of having half transfer interrupt. So that we can handle half the data, while the DMA keeps on receiving the second half. This is it for the UART DMA. The same logic can be used across all the peripherals. The DMA settings will remain same, and all you need to configure is the source address, and the destination address. The peripheral address in almost all cases is the data register of the respective peripheral. That's all for the video. Leave comments in case of any doubt. You can download the code from the link in the description. Keep watching, and have a nice day ahead.